Pleasing the cop. Consider a car that's already in motion and approaching a stop sign. Car moves with a constant speed for 5 seconds. The driver thinks he can run the stop sign. Driver sees a police officer watching the intersection, so the car slows to a rest. Then the car is at rest for a single instant, so the officer is happy, and the car accelerates again back to its original speed. The velocity versus time graph looks like this. Constant velocity, positive and constant. Therefore, the position graph's slope is initially positive and constant. Now the velocity graph's value is decreasing to 0. So the position graph's slope decreases to 0. How do we know to put in that bend there? Well, you have to think about it. We're going faster at this end than we are here. So naturally, the only way to put in that bend, that curve on our position time graph is to show that with the bend by connecting those 2 points. Finally, velocity graph's value is increasing from 0. So the position graph's slope increases from 0. Velocity graph's slope is initially at 0. Guess where the acceleration is going to be? 0. Velocity graph's slope is now constant and negative. Guess what our acceleration will be? Constant and negative. Velocity graph's slope is now constant and positive. Guess what our acceleration will be? Constant and positive. Notice the velocity vector increases as the car speeds up and decreases as the car slows down. By the way, I'm no police officer, but I cannot imagine that stop being sufficient. I feel like you're not entirely stopped. If I were a police officer, I might be inclined to ticket this individual. How the velocity graph's value, notice how the velocity graph's value increases as the car speeds up and decreases how the car slows down as the car slows down. Notice how the position graph's slope increases as the car speeds up and decreases as the car slows down. How do you know if a slope is increasing or decreasing? Remember, horizontal line, that's a 0 slope. So are you getting closer to that horizontal line, or are you getting further away from that horizontal line? If you're getting closer to the horizontal line, then that means you're getting closer to 0. That means your velocity is going to be decreasing. Notice how the car never moved backwards, so the velocity is always positive. Notice how acceleration is positive as the car speeds up and negative as the car slows down. Dare I put 2 examples in the same video? Oh yeah. Wrong turn. This is the last example. Driver takes a turn and immediately realizes this is a dead-end road. Car initially accelerates from rest for 5 seconds, then realizes that this is a dead end and slows to a rest, reverses direction over the next 5 seconds, then the car comes to rest for another 5 seconds. Velocity versus time graph is going to look like this. Oh, there it is. We've crossed over the x-axis. We've gone into 0 world, or negative world over here. So that means we have changed directions at exactly this point. So if you had a question, what time did this car change directions? Then it's going to be 7.5 seconds. Velocity graph's value is initially at 0 and increasing to become positive. Therefore, the position graph's slope is initially 0 and is increasing to become positive. Remember, the slope of a position versus time graph is your velocity. So if your velocity starts at 0, then your slope starts at 0. If your velocity is increasing, then your slope is increasing. an increasing slope is getting closer to being vertical, undefined slope. Now the velocity graph's value decreases back to 0. So the position graph's slope decreases to 0 smoothly. Now the velocity graph's value goes from 0 to negative. There's our change in direction. So the position graph's slope goes from 0 to a negative. From 0 to a negative. From 0 to a negative. 0 to a negative. Finally, the velocity graph's value goes from negative to 0. So the position graph slope goes from negative to 0. This is a lot trickier than the previous examples for sure. Make sure you have this down. Graphs and reading graphs are so important. They pop up all over the place, and by getting a strong understanding of this, even if you have to go through this entire lesson again, I would do that. I'm not done yet. Relax. Don't hit stop. I'm not done yet. But I feel like you're able to build on this later on through the year. So if you get this down really well, if you can translate between these three graphs, then you shouldn't have a problem with any graphical problem that will come up later on in the year. And there will be plenty. Initially, the velocity graph's slope is constant and positive. Our acceleration will then be constant and positive. That's right. Good. Now, we're crossing that 0. But does that affect our acceleration? The slope is a steep negative, so the acceleration is just going to be negative. Notice that it's a straight line. This crossing the x-axis only affected this position graph. That's where the change in direction is noted. Acceleration is still just this whole big line segment. Finally, the velocity graph slope is the same positive that it was initially. Parallel lines. So the acceleration's value is the same constant positive it was initially. Here's the cartoon. And some things to recognize. The velocity vector increases as the car speeds up and decreases as the car slows down. Makes sense, of course. We've seen that a lot now. This is the first time where we're changing directions. Did you notice how the velocity graph's value increases as the car speeds up and decreases as the car slows down? Did you notice how the position graph's slope increases as the car speeds up and decreases as the car slows down? Notice how acceleration is the same direction as velocity as the car speeds up and opposite direction of velocity as the car slows down. This is a really good chance to take a look at that. Acceleration in the same direction as velocity, we're speeding up. Acceleration in the opposite direction as velocity, we slow down. And then we speed back up, and then we slow back down.